Yeah, so we will wait for 1 or 2 more minutes more. Let's see how many joins. Then I will start the session. Hi, am I audible? If you can confirm even in the chat if I'm audible or not. Yeah, so we'll start, let's say, in 1 or 2 minutes more. Okay, so let's begin. So, hello everyone, my name is Rajan Mukherjee, and I'll be taking this for live session for NPTEL course on operating system fundamentals. This is a doubt clearing session, and this session is being recorded. You can watch it after the class is over on YouTube. So I'm a research scholar at the Department of Computer Science Engineering, IIT Kharagpur. So we'll be discussing the topics that are covered this week, as well as some of the sample problems that I have prepared for this one, which will be very common to this week's assignments as well as your end exam. So let's begin without any delay. In this week, we were introduced to mostly two topics. One was the pending part of last week, that was Dynamics philosopher problem. Another part was the deadlock. So, in Dynamic philosopher problem, so last week what we are basically discussing. So, uh, in the last few weeks, uh, we discussed our problem, that is mutual exclusion. And critical section. So uh, we discussed that any synchronization problem should have these conditions satisfied, like mutual exclusion, critical section, etc. So one, we went through the topics uh, like our extra topics, like we went through producer consumer problems, reader writer problems. We went through this problem and we solved it using mutex lock and monitors to solve the synchronization problem, where we discussed to end the critical section can be in achieved for critical section problem. Mutual exclusion should be provided. So as a result, only uh, one process can enter the critical section at a time. So this is a famous problem that we will discuss here. that is known as the critical section problem. So in critical section problem, in this dynamic philosopher problem, what we have is a what we have is few diners. Let's say 5 diners we have, and we have 6 chopsticks, One, two, three, four, five. Sorry, yeah, 5 chopsticks. Now these are placed like on both sides of, so for this diner, one chopstick is placed here and one chopstick is placed here. So here is their food, right? So they want to eat their food. So to eat their food, they need 2 chopsticks. So for suppose this person, let's say P1, P1 picks up these 2 and 3 chopsticks and he starts eating. So at the same time, uh, now at that time, let's say P2 cannot pick up these chopsticks, right? Because it doesn't to eat, it will not be able to eat because it doesn't have both the chopsticks. So here the chopstick is basically the resource, and we declared a semaphore against it, against a chopstick. So to eat, basically you need 2 chopsticks. So what does he do? So what is the problem here? So we have 5 chopsticks and 5 person. Now naturally all of them will not be able to eat together as a result of this, because there are scarcity of chopsticks for each person. Each person needs 2 chopsticks to eat, and only those available one beside the other will be able to pick it up. So the algorithm is uh, uh, like this. So we uh, take one chopstick, the philosopher takes one chopstick, philosopher I, and the one beside it, I plus 1 mod 5. Then he eat, and then after that he signals that okay, my chopsticks, I have completed eating and I am releasing this chopstick. Okay, so this is the structure of your philosopher. So it picks up a chopsticks, 2 chopsticks, it eats, and then it signals that okay, my eating is done, so I am leaving. So now this solution guarantees that no 2 neighbors are eating simultaneously. So this means, so when P1 is able to eat, P2 is not able to eat. Again, P3 is able to eat because it can pick up this one. Again, in that case, P4 will not be able to eat, and as well as P5. So you see, no two consecutive philosophers are not able to eat. Only there has to be some gap between this. Or let's say like when P1 is eating, P5 and P2 are not able to eat. So and only one out of P3 and P4 will be able to eat. So at a time, only 2 will be able to eat. So this solution guarantees there are 2 neighbors eating simultaneously, and the problem remains there is a possibility of a deadlock. One deadlock happens. Suppose all 5 philosophers become hungry at the same time, and each grabs each grabs the left chopstick. Okay. So what happens is here. So here is philosopher I. So here you have your. So here is P1, P2, P3, P4, P5, and also you have chopstick is C1, C2, C3. Sorry, let me rename it. C1, C2, C3, C4, C5. So suppose like all philosophers become hungry at the same time and they pick up the left chopstick. So what happens? P1 P1 gets C1, P2 gets C2, P3 gets C3, P4 gets C4, and P5 gets C5. Now to eat, it requires the chopsticks to its right as well. But what happens when these all happen simultaneously? See, P1 will not be able to eat because it requires C2. So, and C2 is currently occupied by P2. Again, P2 will not be able to eat because it requires C3, but C3 is currently occupied by P4. Again, P4 is not able to eat because it has C3, if C4, but it doesn't have C5 because C5 is currently held by P5. So as a result, none of this results in a deadlock, that none of them are able to grab the right chopsticks. They only have one chopstick at a time. So what is the solution? Allow at most 4 philosophers to be sitting simultaneously on the table. Allow a philosopher to pick up the fork only if both are available. So so it does not allow to only pick up one chopstick. So at a time you have to pick up both chopsticks. If you pick up one chopstick and found that the other chopstick is not available, you release your chopstick and let the other person complete it, and when both are available, only that time you pick it up. Or use an asymmetric solution where odd number philosophers pick up the left chopstick and the right chopstick simultaneously. So by numbering, you basically giving a priority to which one to pick up and which one not to pick up. So that is your diner philosopher problem, and with that you come to the end of deadlock. Any doubt regarding a diner philosopher problem, you can ask. Okay, so that ends your process synchronization problem and all. We discussed mutual exclusion, critical section, and the solution for all of those critical section problem, bounded weight, progress, all three we have discussed completely. Now let's jump to this problem of deadlock, which we have encountered where when solving these various algorithms of mutual exclusion and all, mutex and monitor. So now we come to deadlock. So as we see in the dining philosopher problem, what happened is you have, let me draw it once. So you have a table, you have like philosophers, P1, P2, P3, P4, and P5, and you have 5 chopsticks simultaneously. C1, C2, C3, C4, and C5. So we saw that for each philosopher, P1 P1 needs, if P1 captures C1, P1 needs both C1 and C2. But if C2 is not available and P2 has taken C2, so it is at the point holding one resource, and it is asking for this resource too, which is currently held by P2. So that is a deadlock. So it is not able to guarantee that, it has to wait. So this is a basically a circular deadlock. So so this is how this dining philosopher problem is a very good example of how deadlock occurs. So basically you have five processes which requires uh, so so basically your five processes. P1 requires P1 requires C1 and C2. P2 requires C2 and C3. P3 requires C3, C4. P4 requires C4, C5, and P5 requires C5 and C1. So what happens the problem when all of them try to enter the critical section at the same time, but it acquires only one resource. So P1 acquires C1, P2 acquires C2, P3 acquires C3, P4 acquires C4, and P5 acquires C5. So in that case, what happens? So the processes, all of these five processes, basically are waiting for all of these five processes are basically waiting for other process, other resource to acquire other than the one which it has already acquired. So P1 has acquired C1, P2 has acquired C2, P3 has acquired C3, P4 has acquired C4, and P5 has acquired C1. But all of them requires one more resource to enter into it, but all of those resources are currently held by other processes. So P1 requires C2, but P2 is currently holding C2. So as a result, C2 P2 requires C3, but it is currently held by P3. So all of them are holding on to its own resource. All of the process are holding its own resource as well as claiming other resource which is not available. So all of them just remain in the state of called deadlock because they are not able to acquire the other resource. That is the problem of how deadlock occurs. Okay, so that is the main crux of your deadlock. Uh, a typical example is your a typical example is your traffic grid where let's say this car needs to go, but this is going that side. This car needs to go, but like this car needs to go, but this is the traffic is going this side. This side. This car needs to go, but the traffic is going this side. Again, this car needs to go, but the traffic is going this side, and it's just in a loop that no one is not going able to get out of this loop. That is what your deadlock means. Okay. So this is typically your like I will call them your data elements, like data elements for any deadlock algorithms, deadlock prevention, detection, etc. So you have your resources types R1, R2, Rm. So these are various resource types. So they can be CPU cycles, they can be memory space, they can be IO devices. Resources can be anything. It can be CPU cycles, it can be memory, it can be IO devices. So let's say you have a process P and you requires access to both printer, you require access to printer let's say X. So that is printer is a resource for that process. Each resource type has WI instances. So each resource type, let's say printer, there are three printers maybe. So if you go to any Xerox shop or something printout document or shop, you can find that there are more than one printers available, and all are connected to the same same PC. So so resource type Ri may have three printers. So a process utilizes a resource as follows. It requests for the allocation of that resource, it uses that resource, and then releases the resource. That is how your system model for any any kind of processes. Okay. So any doubt understanding what is a deadlock or uh, these terminologies, because we will be using these same terminologies for the rest of the discussion today. If you have any doubt, you can ask. Okay, so let's go to the next one. So we will look at an example of deadlock, like it is similar to what we have already seen. So this is your, so it is called thread. So let's say this is your process one, and this is your process 2. So you have it uses two mutexes. This is first mutex and this is second mutex, and again it uses two mutexes, second mutex and first mutex. So simultaneously we enter like it executes both processes. It comes here, process P1 acquires first mutex, and process P2 acquires second mutex. Now what happens? So now it requires second mutex, P1 requires second mutex, and P2 requires first mutex. But they can't get it because P1 is hanging on to the first mutex and P2 is hanging on to the second mutex. So neither of these calls, neither of these processes are becomes waits on this part of the code, and it is not able to access the rest of the code. So both of the programs gets locked simultaneously and is not able to go beyond those locks, this part of the locks, right? So that's the issue. That's the issue of how deadlock occurs when you are using a mutex lock or monitor or any those kind of things. Okay, so this is an example of your deadlock, quite similar to the dynamic philosopher problem, where the where you have to acquire both the chopsticks to eat, otherwise you are not able to eat your rice. Okay, so these are the characteristics of deadlock. So deadlock can arise if any of the four conditions are hold simultaneously. So one is mutual exclusion. Mutual exclusion, it has to be mutual exclusion. These may be called a characteristic, but critical section problems should have mutual exclusion, right? So you can say it is a boon or a curse, but that it is what it is. Mutual exclusion, that is only one process at a time can use a resource. Hold and wait. So our process P1 process is holding at least one resource, and it is waiting to acquire additional resource held by some other process. So it is similar to the dynamic philosopher problem, where philosopher 1 is holding on to chopstick 1 and it wanting C2, but C2 is currently held by, let's say, P2, which is now eating, let's say, this using C2 and C3. So P2 wanting C2, but currently P2 is currently held by this, C2 is currently held by P2. So that is your hold and wait. So our process is holding at least one resource, is waiting to acquire additional resource held by another process. Now what is the problem? If P2 is currently eating, and because P5 comes, P5 requires C5, but it also requires C1. So it is not able to, but it is not able to get C1 because C1 is currently held by P1. So these two processes are not able to like go beyond because they are in deadlock of, because their resources are currently hold on to some other resource. So that is characterization of deadlock, hold and wait. Another is preemption. A resource can be released only voluntarily by the process holding it after the process has completed it. So no preemption is means that P2 will release C2 and C3 only when its eating is done. Okay, fine. But what is the problem with P1 if there is no preemption? Because currently it is holding on to C1 and it will not release C1 unless and until it has completed its task of eating the rice. But how can it eat the rice? Because C2 is currently not available to him. So a resource C1 is not released voluntarily, is released not voluntarily because it is not able to complete the task. Whereas C2 and C3 will be able to be released by P2 when it completes its task. That is your condition of no preemption. So all these four properties are very important as you go further for any exams related to this OS. These deadlock coordination are very important. Another is your circular weight. Circular weight we have already seen is in your dynamic philosopher problem. So there exists a set of waiting processes such that P1 is waiting for a resource currently held by P1, P1 is waiting for a resource currently held by P2, and Pn is Pn minus 1 is related by the host, that is by P1, and Pn is waiting for a resource that is currently held by P0. Basically it's a circular weight where in your dynamic philosopher problem P1 was waiting for C2, P2 was waiting for C3, P3 was waiting for C4, and on. So if you remember, if you check this here, P1 basically wants C2, P2 basically wants C3, P3 basically wants this one C4 and all. So there lies the problem of your circular weight. So this dynamic philosopher problem is a particularly interesting case of your circular weight problem. Okay. So these are your four conditions. Let me know if you have any doubt. Okay, so let's go back. So now we will be introduced to something called resource allocation graph. So a resource allocation graph, there are two types of vertices. So what is a graph? I hope you know what is a graph. Let me give you an example first. So in a graph, you have a sets of vertices. So you have a sets of vertices. So these are vertices V1, V2, V3, V4, and the sets of edges E1, E2, E3, E4. So these are so this is a graph G which consists of V and E. right? So this is your graph. Now uh, now we will discuss what is a resource allocation graph with respect to your uh, this deadlock detection and everything. So a resource allocation graph has its V, but it has currently of two types. So one is the process graph, that the set containing all the processes, and you have your resource graph, that resource vertices, that the set consisting of all types of resources. Now, if there is a directed edge between request edge, so request edge means that P1 PI is requesting RJ. So then you have a edge from PI to RJ. But if PI is using, it has been currently assigned to him RJ, then you have the direction in opposite way. PI that arises from RJ to PI. Okay, so that is your the structure of your edges. So you have your two types of resources, P1, P2, P3 dot dot dot, and R1, R2, R3. So P is your processes and R is your resources. Okay, so this is your like like all the variables for your resource allocation graph. Now let's look at our resource allocation graph, how the other particle looks like. So a process is denoted like this, our resource is denoted like this. Here this 4 dot means there are 4 instances. So a printer, let's say you have a printer, so printer is your resource. Let's say resource is printer. This means there are 4 printers available. Okay, so this means there are 4 printers. Always remember R, R1, R2, R3 are the types of resources, not the resources itself. So R1 may represent printer, R2 may represent keyboard, R3 may represent let's say a camera, like video cam, those kind of things. So there are different types of instances basically. Okay, now our request instance is like this, from PI to RJ, and holding instance is like this, RJ to PI. Okay, that is your resource allocation graph. Now here is an example of a resource allocation graph. So what does this indicates? This indicates there are one resource, resource type R1 has one instance, resource type R2 has 2 instance, resource type R3 has resource type R2 has 2 instance, resource type R3 has 1 instance. Sorry. And resource type I4 has 4 instances. So what does it mean? This means P1 is currently holding, P1 is currently holding 1 instance of R2 and requesting 1 instance of R1. See, P1 is holding 1 instance of R2 and it is holding currently 1 instance of R2 and it is currently requesting 1 instance of R1. Okay. Similarly, here P2 is currently holding 1 instance of R2 and 1 instance of R3, R1. P2 is also requesting 1 instance of R3. So it is holding R1 and R2 one instances each, and it is requesting one instance of R3. P3 is currently holding one instance of R3. So this is an example of your resource allocation graph. So any doubt understanding the resource allocation graph? Let me know. Okay, so let's come back to it. So these are the basic fact. So if a resource allocation graph has no cycle, then there is no deadlock. If a resource allocation graph have no cycle, that means no deadlock. If a graph contains a cycle, if one instance per resource type, if only one instance per resource type exists, then there is a deadlock exists. This is, let's say, 1.1, this is 1, this is 2.1, and this is 2.2. If several instances per resource type, then there is a possibility of deadlock. Okay, we will come back to one of them each at a time. So consider this graph. Does a cycle exist? Does a cycle exist in this graph? If you notice, yes, there exists a cycle. There exists a cycle. This is a cycle. So in this graph, what is happening? P4 is currently holding one instance of R2, and P1 is holding one instance of R2. P3 is holding one instance of R1 and is requesting one instance of R2. P1 is wanting one instance of R1 and one instance of R2. So here a cycle exists. Yes, a cycle exists. But does deadlock exist? Now the question is, does deadlock exist? Does deadlock exist? So we will come back again here. So graph contains a cycle, yes. If several instances per resource type, yes, there are more than one instance per resource type. There is 2R1 and 2R2. Then there is a possibility of deadlock. Then there can be a deadlock. A deadlock may exist or deadlock may not exist. So let's look at this graph and determine whether a deadlock exists or not. So what happens? P1, so consider this process, P2. P2 will run its course and complete R1. Okay. P2 completes R1 and P4 completes R2. Then what happens? One resource of R2 and one resource of R1 becomes free, right? So this resource and this resource becomes available. So at that time what happens? P1 can get this R1, this free R1, and P3 can get this free R2. So as a result, at that time both P3 and P2 will get get both R1 and R2, and it will be able to complete the processes. So therefore, even though there is a cycle, even though there is a cycle, even though there is a cycle, there is no deadlock. Even though there is a cycle, there is no deadlock. Okay, so this condition, that if several instances per resource type, then there is a possibility of deadlock. So there was a possibility of deadlock, but as you can see, there is no deadlock in there, even though there is a cycle, right? So if there is no cycle, that means there is no deadlock. But if there is a cycle, if there are no instance, there is single instance, then there is a deadlock. But if there are more than one instance, then there may be a deadlock. And we saw here that a deadlock does not exist even though there is a cycle. Okay. So any doubt regarding this graph and how we described that it doesn't have a deadlock? Okay, so let's go to another example. Now consider this one. So here you have three resources and three processes, P1, P2, P3, and basically four resources, this four. So the question is there a deadlock here? Now here you see P1 is currently holding on to R2 and is requesting R1. R1 is currently held by P2 and P2 is currently holding also R2 and is requesting R3. Now then there is this one, R3, P3 is holding R3 and requesting R2. Okay. So here, does a cycle exist? Does a cycle exist? Answer is yes, because here is your cycle. Okay, so your cycle exists. Now there is a cycle exists. Now there is more than one resource type here. Okay, there is more than one resource type. Now we need to check whether our deadlock exists or not, because now there is only we know there is a possibility of deadlock, but the deadlock may not be present also. Okay, so let's look at why deadlock here occurs or not. So what happens here? P1, P2 is currently holding on to R2 and R1 and R2, and it needs R3. So P3 cannot fulfill it. P1 also cannot complete it because it needs R3 and R2, but R2 is currently hold, and P1 requires R1, which it doesn't have, but it has an R2. So yes, so here there is a deadlock. Because none of them are able to give up their own resource without with completion, and for solving this you have to give up some of the resources, otherwise not. Each one of them is holding on to some resource. So yes, a deadlock exists here. Okay, so any doubt regarding this? Any doubt regarding this allocation graph and everything? So here we found a cycle exists, there are multiple resources and a deadlock also present. So any doubt regarding this deadlock and resource allocation graph? Okay, so let's get to some other issues. So there are three ways to handle deadlock. So to handle deadlock, there are three ways. So here you have to handle deadlock. One you have prevention, two avoidance, and three detection. So, as the name suggests, prevention and avoidance are totally depends on prior knowledge of your system. Like you have to know that how your system works. Whereas in detection is like post like after the deadlock has been found, then you to found that any deadlock occurred or not, and after that you take some action against it. So one is a aggressive, another is a passive. Others are passive. So if you look at this, so this helps our system to enter a deadlock state and then get recover, those kind of things. So these three techniques we will next discuss. So what is deadlock prevention? So it ensures that at least one of the necessary condition of deadlock doesn't hold. So we have seen all the conditions for deadlock. What are the conditions? One, mutual exclusion. Number two, hold and wait. Number three, what is number three? No preemption. And number four, circular wait. So for prevention, each one of them has their own technique. Now the problem with mutual exclusion is you require mutual exclusion. You cannot get away with mutual exclusion. It is a boon as well as a curse. So okay, mutual exclusion sometimes leads to deadlock, but you cannot get away with mutual exclusion. You have to require mutual exclusion. Otherwise, your critical section problem will be a vague one. The critical section only does not exist if you doesn't provide mutual exclusion, and as a result, deadlock doesn't even come into question. So mutual exclusion cannot be prevented. You have to use mutual exclusion. That is a hard and fast rule. Now, what about hold and wait? So what is happening in case of hold and wait? So a resource has been acquired by one of the processes, and it requires another resource. It needs more resources that is currently doesn't have, and some other process maybe have holding on to it. So it was something like this, right? So let's say P1 has requested C1 and C2. Okay, it has got C1. It has got C1, but it has not been able to get C2 because C2 is currently acquired by P2. C2 and C3 is currently acquired by P2. So P1 has to wait. But if someone else, like C2 and C3, suppose P4 currently needs C1, then what will happen? This one will also wait, this one will also wait. But C1 can complete it because if P1 releases it. So in hold and wait, what happens? So when a process is requesting some resource, the thumb rule is it can be allocated all the resources at a time, such that this part of acquiring one after the another are not. So if P1 requires P1 requires C1 and C2, so if P1 requires C1 and C2, P1 has to get C1 and C2. If it doesn't get, it releases both C1 and C2 directly. If it doesn't, if it is able to get only C1 or C2, only one of them, then it releases the hold, and it tries after some time. So that is how you prevent your hold and wait condition. Okay. So let me repeat it once. Okay, it's a little confusing, but So you have P1. P1 requires C1, C2, C4 maybe, let's say. You have P2 which requires C2, C3, C5, C6, C8, and there is P3 which requires C1, C7, etc. And let's say C9. Okay. So now P1 and P2, let's say, start simultaneously. P1 acquires C1, P2 acquires C2 and C5, and P1 after that after that what happens? Since P1 is not able to get C2 because C2 is currently held by P2. Now suddenly let's say P3 arrives. So here, so in this case, P1 is in wait state with C1 because it is not able to get C2, which is currently held by P2. Now what will happen to P3? P3 requires C1, but C1 is currently in, held by P1, and P1 is in wait state, so it is not able to get it, right? So here is the deadlock basically. So what does the prevention scheme will do? So what does the prevention scheme will do? That unless and until you are able to get all the resources, you are not given a single resource also. So you have to acquire all at the time, not one at a time. So if you're not able to get it, you will release all the resource and then go back. So here, since P1 is not able to get C2, what it will do is it will release C1 also, and then it will go to the wait state, and since C1 is currently released, P3 will run to completion. So after P1 and P3 gets over, then P1 can be scheduled. P1 can be scheduled. So that is how your deadlock prevention occurs when you have to prevent hold and wait. Okay. So you do two things. One, you release all the resources as if you are not able to get a single one. If you are not able to get all, and if you get all, then only you can be able to progress. So any doubt regarding this? Next is no preemption. So how to prevent your no preemption? So to prevent no preemption, what we'll do is so if a process A, something is holding some resources and request another resource which is not allocated only, then the resource currently held by A are released. So it is kind of similar to your hold and wait. So suppose P2 is currently using all these resources, and suddenly you come here and you request C1, you get C1, but if you request C2 is not currently available. What you will do is you will release C1 and C1 and just wait. So these two are very common. So either you are allocated all the resource when you are accepting it, or else preempt it. That is what it does. Okay. So these are the two ways of getting your resources. So and last one is circular wait. To prevent circular wait, what we do is you name all the resources in some order. Let's say priority order: R1, R2, R3, R4. So any process PI that requests it will be allocated all the resources, let's say, which are less than equal to that index. Okay. So priority of acquiring which processes can P1 can occur or P2 can occur will be set previously. so that there is no deadlock while acquiring. So that is how yeah. Am I back? Yeah, okay. So as I was saying that in circular wait, basically you have each process has been given some priority. So okay, so and resources allocated to it. So also have some priority. So a process in a or in an order will be able to acquire only the process within its priority and then leave. Okay, so that is how your circular wait occurs. So if you check it, so basically we impose a total ordering of all the resource types and require that each process requires resources in a increasing order of enumeration. So we impose a total ordering of all the resource types and require that each resource type requests in a increasing order of enumeration. Okay, so that is previously determined. Now, what is the problem with this prevention scheme? So the problem with this prevention scheme are you need to set your priorities beforehand, that how to do, what to preempt, when to preempt, what order it should be allocated resources. It has to be known previously. That means whenever you are running a process, the process need to know whatever resources it need. So you need to completely know up to its run of course what are the processes it need or not. But actually that is not the case how your program works, like your big servers and all. Their process runs from its start to end, and it doesn't know like it is not your simple C++ program that you stop it after every execution, that runs forever. So what will that doesn't know what resource will come when and what. So that's why these prevention schemes are not suitable for those kind of problems. It is not at all suitable. That is not mostly used. Okay. So how? So we come to the next kind of technique to that is called deadlock avoidance. So ensure the system never enter a state of deadlock. Like previous one, this one also requires a priori information of all the possible resources request that can be requested. A simple and most useful model requires each process declare the maximum number of resources of each type that is needed. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Resource allocation state is defined by the number of process available and the maximum number of demands of the process. So we'll come to all of them at a time using some examples. So bear with me for that time being. So I know this is a very big heavy kind of words, but when you see through an example it will be much easier for you. Okay, so what is a safe state? So the safe state is a system is in a we call system is in a safe state if there exists a sequence of processes in the system such that each process pi, the resource that pi still request can be satisfied by currently available resource or can be held by pj. So our system is in a safe state if there is basically no deadlock, if there exists a sequence of processes of all processes in the system such that for each pi the resources can still request can be satisfied. Okay, so that is if pi resource needs are not immediately available, pi can wait until all resources pj are finished executing. This is point number 1. These are the points which you require to remember. When they are finished executing, they release all the resources, that then PI can obtain the needed resources, execute and return the allocated resources and terminate. This is your point number 2. When PI terminates, PI can obtain its needed resources and carry on. This is your point number 3. So PI needs resources are not immediately available, then PI will wait until all the processes PJ are finish executing. When they are finished executing, they release all their resources, and PI can obtain the needed resources, execute them, and return the allocated resources and terminate. And when PI terminates, PI1 can obtain its resources, and the show then goes on. Okay, that is your safe state. Any doubt regarding this? Okay, so let's go to some examples. So the basic fact is, if a state is in safe state, then there is no deadlock. If a state is in unsafe state, then there is a possibility of deadlock. And this part is important. There is a possibility of deadlock. There can be a deadlock but cannot be a deadlock. But if the system is in a safe state, then there is no deadlock. Remember, these are why this question mark happens, that if there is an unsafe state, then there is a possibility of deadlock. The problem is, here you need to get what are the types of resources and how much the resources are required a priori. It needs to the system needs to operating system needs to know it a priori, that what this process resource requires the resources and what kind of resources it requires. So all these algorithms are quite approximate algorithm, and so the result, if the result is in a safe state, system is in a safe state, then there is no deadlock. But if it is an unsafe state, then there is a possibility of deadlocks. That is the fact. Now, deadlock avoidance algorithm, we'll come to it. So we'll use this called Banker's algorithm. So now this resource allocation graph scheme have some extra mileage we'll add. So you have your original resource allocation graph. Now we will add something called claim edge. So claim edge is, there is a edge from PJ to PI indicate that the process PJ may request the resource RJ represented by a dashed line. This dashed line is important. So if you look at this diagram, this means let's define it. P1 is holding, let me draw it on the figure itself. So this means P1 holding R1, P2 requesting R1, P2 claiming R2, P1 claiming R2. Okay, so that is basically it is here. So that is what it says. The claim edge indicates that a process PJ may request a resource. So this means a resource has been already allocated. This means you are requesting, and this means in future there may be a request. Okay, so that is why it is quite in a way our system doesn't know that whether it will claim it or not. So this is a priori algorithm. Again, the problem with a priori algorithm is basically you need to know beforehand what the resources is required or not. So this is how you represent it. A request stage is converted into an assignment age. A claim age converts to a request age when a process requests a resource. Request age is converted to an assignment age when the resource is allocated to the process. When a resource is released by the process, an assignment age reconverts into a claim age. That is what it requires. The system must know a priori in the system. The resources must be claimed a priori in the system. A cycle in this graph implies the system is in unsafe state. If there exists a cycle, which there is no cycle here, then this is in a safe state. Now, if you look at this graph, there is a cycle. So, it is in unsafe state. Is there a deadlock here? Yes, currently there is a deadlock here because P2 wants R1, P2 wants R1 and holding R2, P1 holding R1, right? So that is your, so if this request is not made, if this claim doesn't convert into a request, if claim not converted into request, no deadlock, else a deadlock. So suppose a process PI request a resource RJ, the request can be only be granted if the converting request age, if converting the request age to an assignment age doesn't result in the formation of the cycle in the resource allocation graph. Otherwise, the process must burst. Okay. So when you are converting an age request age to an assignment age, if it doesn't result in the formation of a cycle, then it is it can be granted, the request can be granted, else the process must wait. Now let's come to the banker's algorithm to solve this deadlock avoidance problem. So in a banker's algorithm, you have multiple instances of a resource type, same thing which we did previously. A process must have an a priori claim maximum use. When a process requests a resource, it may have to wait. If a process gets all its resources, it must return them in a finite amount of time. It is kind of simple to like your interest-free bank, where customer establishes a line of credit, borrows money in chunks, and together never exceed the line of credit. Once it reaches the maximum, the customer must pay back a finite amount in a finite amount of time. It is completely how your banking system works. You take a money, but you never your credit card. You take a money, but you never exceed your credit limit. Then once it reaches the maximum, the customer must pay back in a finite amount of time. So let's now discuss the banker's algorithm in details. So you have the following data structures. That is, you have n number of processes, m number of resource type. You have an available vector, which denotes the instances of type resources. So like for each resource type, the amount that is available. Then you have a m comma n matrix. That is the max allocation that can be given. This represents then you have an allocation matrix. Then you compose the need matrix, that is your max matrix minus the current allocation matrix. Okay, we will discuss with example this one. So we define two more vectors. work and finish. Work is the current available, finish is false for all the processes first. So for each I, such that finish is false and need is less than equal to work, we select them. If there is no such option is present, then we come here. If there are option present, then what we do is we complete those allocation and say that this is true. So what does this does? This does basically, you have a resource list available. You check whether process P1, which has a claim of something, you see whether this is able to satisfy this, is need cover all its claim. If it is able to cover all its claim, then we say that okay, this is done, and we add this to this. Yes, we add the work to this allocation, and then we mark it as that it has been completed. Okay, that is how it gets done. So bear with me that if there is confusion arising, I will give it an example to solve it. Okay, so let's come to this example. So let's say you have a claim matrix. You have a claim matrix. P1, P1, P2, P3, and P4, and you have resources R1, R2, and R3. Okay, so let's fill these matrices 3, 2, 2, 6, 1, 3, 3, 1, 4, 4, 2, 2. And then you have your allocation matrix that represents the current allocation. It will become something like this. P1, P2, P3, and P4, R1, R2, R3, 1, 0, 0, 6, 1, 2, 2, 1, 1, 0, 0, 2. And this is your available vector currently. 0, 1, 1, R1, R2, and R3. Okay, so now we will apply the banker's algorithm to solve this issue. So solve whether this is a like this can be, so this like this can be this is a safe state or not. If this is a safe state or not. Okay, so first we will do is this. What we will do is this is C, let's say A. So we will find out the need matrix, which will be C minus A. Okay, so let's find out the need matrix. Need will be C minus A, which will come out to be something like this. So C minus A, that will become that will become 2 2 2 2 2 2 6 1 3 6 1 2 minus this, that will become 0 0 1. Then you have this minus this, 1 0 3 1 0 3 2 2 0. This will be 4 2 0, and your current available is 0 1 1. So you check which of these will complete if we apply this vector. So you will check that P2 will complete first. So P2 will be the one which require only one instance of R3. We'll use this and complete. So after this, what will happen? Whatever P2's allocation was there, this claim will be added to this available matrix. So it will become 0. It will become. Let me one more. Yeah. So we'll add this 2 1 1 to it, this allocation part to it. So 2 1 1 plus 0 0 1, 2 1 1 plus 0 0 1 will become 2 2 2. And if you see, that is what P1 wants. So next P1 will run to completion. So after P1 runs to completion, it will become, we will add P1's allocation, that is currently 1 0 0. So it will become total 3 2 2. Okay. Now which one will complete next after this? Sorry, I made a mistake. So first, let's try again. Available factor is 0 1 1, R1 R2 R3. Okay. Now, so our P2 will be the one which is first completed. Okay. So P2 will be completed first. So we will add its allocation to it. So what was his allocation? 6 1 2. So 6 1 2 will be added here. 6 1 2. So total allocation now will become, available matrix will become after completion 6 2 3. Now we will look at which one will be the one that can go next and complete. P1 can go. Okay, P1 allocation will be completed next because it falls under 1, and we will add P1's one here, current allocation 100, that is 723. After that P3 can go, we add whatever because that allocation is now complete, and P3's current allocation is 211, 211, so it becomes 439. Now P4 has got all the ingredients it need to complete it, so P4 will be the next to complete, and P4's current allocation is 022, 022, so it becomes 9, 5 and 6, which was the initial allocation resource matrix. Okay, so that is how you do this, solve this your Bankel's algorithm problem. Most of the time this question comes how to solve this, and this is how you do it. It was 002 936. Yeah, so any doubt you can ask regarding this. So that is how, so this is your, basically it is able to complete. So this is in your safe state. Now consider a non-safe state example. Suppose we use this only, but we change it a little bit. Now let's say the initial allocation becomes something like this. Yeah, so let's say that now the initial allocation becomes something like this. R1, R2, R3, P1, P2, P3, P4. Three two two 613 314 422. This is your claim. Let's say your allocation is something like this now. R1, R2, R3, P1, P2, P3, P4. Okay, so your allocation is something like this: 100, 511, 211 and 002, and your current available vector is this 1 1 2. Okay, so now we will again check whether this is in a safe state or not. So let's check. So first we will do the need. Need is basically c minus a, which becomes something like this: p1, p2, p3, p4, r1, r2, r3, r1, r2, r3. So if you subtract it, it becomes 2, 2, 2, 1, 0, 1, yeah, 1, 0, 1, no, sorry, 1, 0, 2, so it becomes your 1, 0, 2. The other subtracting it becomes 1, 0, 3, and this one becomes 4, 2, 0. This is your need matrix. Now you have been given the available vector as 1, 1, 2. So you need to find out whether this is in a safe state or not. Okay, so if you look at this claim, you see, does any of them run into completion? Yes, none of them run into completion, because all of them requires this P2 requires 2 unit of R2, and none of them has R1 and R2. P1 requires, so P1 will get into completion, right? P1 will be P2 will be done, right? So if P2 gets done, P2 gets done, P2 gets done, we'll add its resources here. So what is its current resources? 5, 1, 1. So that will become 6, 2, 3. Right. Now, will anyone else get complete now? Now you check, nothing else. Yeah, so you see what will happen here: 6 to 3, right? Now 6 to 3 is the current which is available, and P3 will get selected, right? Because P1 will get selected because it requires only 2, 2, and 2 items of each. So it will get selected, it will run its course, and we will add its resources allocated, that is 1, 0, 0. It will become 7, 2, 3, right? And then as usual P3 and P4. So this one is also a safe state, right? That's how you complete it. Okay, so that is your Banker's algorithm. Next, similarly, after, so again the problem with this Banker's algorithm is you need to get this allocation beforehand, that how like how much claim it will make beforehand. Each process will require beforehand. So that's the issue here. Okay, so let's now come to the last part of this, that is your handling deadlock detection using uh, like how to prevent it. Okay, so now we have, instead of a resource allocation graph, we will have a wait for graph. So each nodes are only processes, there is no resource in this graph, this is only wait for graph. So if pi is less than pi to pj are age happens if pi is waiting for pj. So now remember, all of them item are currently the processes running. Previously what was happening, you are before running only you are making a claim that the process will require this amount of resources. Now you don't know what amount of resources it requires. So instead of using a resource allocation graph, we will be using a wait graph. So p1 is waiting for p2, p3 is waiting for this. This will indicate. So maintain a wait for graph. So how to detect for a single instance? Periodically invoke an algorithm that searches for a cycle in the graph. If there is a cycle, then there exists a deadlock. That's the main crux. So if there is only one instance, if there is a cycle, then there exists a deadlock. Now this is a searching in a cycle in a graph requires n square operation. So it is a O(n) square algorithm. Okay. Now for multiple resources, like similar, you will have a available matrix, you will have an allocation matrix, you will have a request matrix. Uh, Instead of a like need matrix, that only becomes your allocation, your request matrix here. There is nothing more about it. And similarly, you will do the same kind of algorithm. Finish is equals to false, and rest is less than equal to work. If no such I exists, go to step 4. So if they are all if all of them are false, then if for any of the finishes is false, then the system is in a deadlock state. If moreover if I is false, then pi is one that is deadlock. Okay, so the algorithm is quite same. Here you are using basically work is equals to available for it. So basically your need matrix in Banker's algorithm becomes request matrix in detection algorithm. Fine, that's all basically, nothing more, and the rest is similar. The algorithm is basically. So you have your, so any doubt so far? Okay, so let's So after the deadlock has been detected, what you will do? So once deadlock is detected, you abort some of the processes involved in the deadlock. Let's roll back. Need to decide when and how often to invoke the deadlock detection algorithm. It depends on how many deadlock occurs and all. If the deadlock detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, so we would not be able to tell which of the many deadlock processes cause the deadlock. So, so basic concept if a deadlock is detected, try to uh, abort or roll back some of the processes involved in the deadlock. So other part is about all deadlock processes, about one process at a time, and which order we choose to abort. Those are the main crux of this, nothing more. So resource preemption, selecting a victim, rollback, starvation. So that is the conclusion. That is the end of deadlock. So any doubt regarding this you can ask. Else we will go back to solving some problems. Yeah, so let's solve these questions. So question is which of the following measures are to be taken as a solution to dining philosopher problem. So we discussed the dining philosopher problem where we have 5 philosophers. P5, P1, P4, P5, and you have the chopsticks C1, C2, C3, C4, C5. So which of the following solution measures should be taken as a solution to it? So provided the fork, option A, provided the fork can be picked up while in critical section, allow the philosopher to pick forks only when both are available. Yes, so it's saying that provided the fork are to be can be picked while in the critical section, allow the philosophers to pick the forks only when both are available. So as we discussed, so one solution was that P1 will pick up C1 only if C1 and C2 both are available. It's not that only if C1 is available, I will pick up C1 and wait for it. It's not. So it will pick up, it has to pick up both C1 and C2. Only if both are available, else it will not pick up anything. So this one is true. At most 4 philosophers are allowed. At most 4 philosophers are allowed to sit at the table simultaneously. Yes, that is also true. At the same time, only if 4 philosophers are allowed to sit, then the solution becomes much more feasible because you will have 5 chopsticks and 4 philosophers. So, or at the same time, always 2 chopsticks will be free for one of the person to it, and so one will be completed, and then other will pick it up. So, this one is also true. So making the odd number philosopher to pick up the left chopstick first and then the right chopstick and vice versa for even numbered. Yes, so it says that odd number philosophers to pick the left chopstick first and then the right chopstick and vice versa for even numbered chips. So what we do is we say P1 that you pick up the left chopstick, that is C1 first and then C2. But for P2 we say pick up C3 first and then C2. So what happens when both are simultaneously existing? So P1 is able to pick up both C1 and C3 first, whereas P2 tries to pick C3 first. So as a result, P1 will get the access. So then it will not be a issue. So this one is also true. So the correct answer is all of the above. All of the above is correct. So any doubt regarding question 1? This is a basic uh, Danny philosopher problem. Let's go to the next question. So you have been given two graphs, these G1 and G2. You need to find out what we can say about the deadlock condition. So, so this is a graph with only one resource, and this is a graph with two resources. So in each case, we will so what will be the thing is, we need to check whether a cycle is present or not. Check whether cycle is present or not. Now this graph has only one resource, and you see that there is a cycle exists. There a cycle exists. This R2, P1, R1, P2, a cycle exists. So G1 is deadlocked. Now what about G2? Now what about G2? Now what about G2? In G2 you see this parts of the graph. You see a cycle exists here from R1, P5, R3, P4 and R4. So you get a cycle here also. And you see here only one instance is there. It is not here two instances are present. Here are only one instance of each resource are present. So G2 is also deadlocked. So what we need to find? We need to find that whether a cycle was present or not. Since a cycle was present in both of them, so both G1 is also deadlocked and G2 is also in deadlock. So the correct answer is option A, both are deadlocked. So any doubt regarding this? Okay, so let's go to the next question. So which of the following problem we might face if we invoke deadlock detection algorithm at arbitrary interval? Option A. So what are the problem we might face if we invoke detection algorithm, deadlock detection algorithm at arbitrary interval? There may be many cycles in the graph, and it will not be possible to roll back the deadlock process anymore. Yes, so if we invoke deadlock detection algorithm at arbitrary interval, so there may be more than one cycles in the graph. There is not only one cycle. There may be more than one cycles. So it will not be able to possible all the rollback anymore. So if you are currently invoking for 10 seconds and suddenly after 5 seconds you again invoke it, so that is not possible. You need to have a fixed gap, not at any arbitrary interval you come and detect the algorithm again and again. So this one is true. This one will happen. There may be cycles in the graph, and we should not be able to tell which of the many deadlock processes caused the deadlock. Uh, that's not true. You will always be able to tell which of the deadlock processes are able to cause the deadlock because you are able to detect the graphs. So this one is false. There may be no cycles in the graph, and thus it will not be possible to know if any deadlock has happened or not. There should be some cycle in the graph, and it is if there is any no cycle in the graph, then it will always be a no deadlock. So this one is false. So the correct one is option A. Oh, sorry. So what you have is so there can be more than one cycles in the graph, and it will not be possible, and it will not be able to tell which of the many deadlock processes have caused the deadlock, right? So this will be the correct answer because there will be more than one cycles, and you will not be able to detect which of the many deadlock processes have caused the deadlock because at every time you will get a particular cycle and you will say only these processes are in deadlock. You are not able to get which all the processes are in deadlock. Okay, so that is the issue. Now let's come to question 4. Again a same thing. Consider the forest resource allocation graph G1 and G2. What can be said of the deadlock condition? So in each case you need to find out whether uh, cycle exists or not. Check cycle exist or not. So in the first graph, does a cycle exist? Yes, a cycle exists. This R1, P1, R2, P3, R1. So a cycle exists. So G1 is deadlocked. But in G2, both are not cycles. So G2 is not deadlocked. So option B is the correct answer. So let's go to the next one next. So which of the following is incorrect about resource allocation graph? If there is only one instance per resource and the graph contains a cycle, then deadlock exists. Yes, this is true. If there is one instance and then there is a cycle, then deadlock definitely exists. If there are multiple instances per resource and the contains a graph, then there is no possible deadlock. No, false. So in that case, you have may contain deadlock. So this statement is false, that there is no possible. If the graph contains no cycle, then there is no deadlock. This one is true. So only incorrect one is option B. Let's go to the next question. So which of the following phenomena are responsible for deadlock? A process is holding, option A, process is holding on to one resource, is waiting to acquire additional resources held by other processes. True. This causes deadlock. This statement is called hold and wait. Only one process at a time can use a resource. True. Mutual exclusion. A resource can be released only voluntarily by the process holding it after the process has completed resources. True. That is no. preemption. So the correct answer is option D, all of them. Okay, so let's go to the next one. So you have been given these columns, you need to match them. Mutual exclusion while considering the case of deadlock prevention. So mutual exclusion is option. So we have seen that mutual exclusion cannot be used for deadlock prevention because it is hold for all non-shareable resources. So option 1 is now hold and wait. Hold and wait, basically if you're trying to prevent it, so we have seen that resource utilization is low and there is a possibility of starvation. And the last one is no preemption, that preventing no preemption is not practical for most systems. Right, so that's your answer. Let's come to the next question, question 8. Which of the following is incorrect about Banker's algorithm? Each process must have a priori claim maximum use. True, this statement is true. Each when a process requests a resource, it may have to wait. True. When a process gets all its resources, it must return them in a finite amount of time. True. So none of the above is incorrect, all of them are correct. Let's come to the next question. Which of the following is incorrect? Simplest and the most useful model requires that each process declare the maximum number of resources of each type that it may need. So simplest and most useful model requires that each process declare the maximum number of resources that it may need. True, that is one type. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure there can be at least one circular wait condition. False. Resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. True. We have seen the claim graph, allocation graph, and the available processes. Last question. In a resource allocation graph, when a process Pi requests a process Rj, the request can be granted if only one cycle is from, no cycle is not allowed, so it is formed in the resource allocation graph. False. If there is a cycle, that means there is a deadlock. The request can be granted only if the conversion of the request stage to assignment stage, if no cycle is generated in the resource allocation graph. Only if the conversion of a request stage on assignment stage, only if the conversion this one is false. The request can be granted only if no cycle is formed in the resource allocation graph while converting the requested age to an assignment age. True. The request can be granted only if the conversion of request age to assignment age at least one cycle is generated. False. Because no cycle is required. Okay. So any doubt you can ask. That's the end of today's session. Thank you for joining. We will meet again next week.